So I'm going to talk to you overall, just give you an introduction about lithium-ion batteries, give you some industrial context of why we at NPL are working on this topic. I'll tell you more about our organization and how we use COMSOL Multiphysics, certainly from my personal perspective, and then try to give you some insight into a specific problem with relation to battery aging and the diagnosis of what is called state of health. Overall, the schematic you see there is giving some idea of what we do. We simulate things, we generate data, and then we try to understand scientific systems with better insight through interpretation on the wide variety of data results that we can extract from COMSOL Multiphysics. So I think it's likely that everybody in the room, almost everybody, is carrying a lithium-ion battery on their property right now, maybe more than one. We are familiar with this technology for rechargeable batteries. If you've been reading the news, you also know that electric vehicles are growing. UK government has a target by 2040 for no new petrol or diesel vehicles to be sold in the UK. So electrification of powertrain, as we heard in the panel discussion on Tuesday, is also progressing very rapidly. Basic concept of the lithium-ion battery here, you can see that you have two electrodes, one in which in the traditional chemistry you keep lithium in a porous graphite material, on the other side in a porous transition metal oxide. It's much more stable in the latter on the left-hand side, so spontaneously it will discharge through the electrolyte and you can extract electrical work. But if we change it around, it's a secondary battery, it's rechargeable, we can put power in and we can recharge. So this is a mostly reversible system that we can work with. There's rapid growth worldwide in the use of electric vehicles. The graph I show you here comes from the International Energy Agency. It's a couple of years out of date already, but that is showing you that worldwide, EU, China, US, all around the world, we are seeing growth in activity in this area. More people are buying and driving electric vehicles at all scales. Batteries age. Again, your personal experience from these, batteries degrade, their performance declines. Also, customers don't like keeping the same car for too long. Maybe 5 years is a typical vehicle lifetime before people start to think they want to trade in and get a new car. So this really positive graph I'm going to disingenuously turn into a not so positive graph by adding 5 years to the axis and changing the title. And this is the waste projection then. And you can see as we move into the early 2020s across the world, we have a big issue around lithium-ion battery waste because of the uptake of electric vehicles for positive environmental reasons. And we learned in school, what do we do with waste? Well, we should think about reducing it, we should recycle, we should reuse. Can we reduce it? No, we are deliberately engaging in having more lithium-ion batteries coming into circulation because in combination with decarbonization of electricity sources, that is going to put us in a strong position for attaining climate change and carbon emission targets. So we've got to deal with this waste. Can we recycle? Well, I'm not going to talk about that today, but there is active research, including through the UK's Faraday Battery Challenge and the Faraday Institution, towards lithium-ion battery recycling. However, it's difficult. It's difficult to separate components. A lot of the insides of lithium-ion batteries are not very nice. So our third option is reuse. If we have a battery which is no longer fit for service in a car, can it be put into, for example, a domestic storage application, a grid balancing application, where the power requirements are lower? And this is where the work of the Lithium Batteries for Second Use project of EMPIR, the European Metrology Program, has come in. NPL is engaged in this program to contribute to measurement techniques to determine how aged is a battery, what could we do with it after it's no longer suitable for use in a car. In order to explain how aged is a battery, we're going to need to do some definitions. And I'll tell you some things maybe you don't know about the way that battery performance is defined. You may understand the idea that batteries have a capacity in units of charge, often in amp hours. However, this is defined really in the limit of zero current, so that we have no losses from the cell, no transport losses, no ohmic losses, no activation over potential for the specialists in the audience. And we define that between voltage limits and not charge limits, because the voltage defines the safety, warranty limits, the performance limits of the battery. So to a typical battery, we might say here that we can go in this range here between 2.9 volts and 4.2 volts. And this is adapted from a COMSOL application library example where we can discharge and we can predict this discharge curve. So we have two limits. We have a capacity in between them as the charge pass, current multiplied by time. Also, we need to think in terms of rate capability. So if I take the same COMSOL model and rather than using a very, very slow current, I elevate the rate of current passed, and we often use these C units in battery science. This just means one nominal capacity per hour, so 1C is 1 hour discharge, 2C is 30 minutes discharge. As you can see, the amount of charge that we can pass before the voltage goes outside of the limit, the performance gets worse as our losses increase as we work the battery harder and draw more power. And so at 4C, from an example from our 1D COMSOL model, you could see that the rate capability here is only maybe about 45% of its nominal value. So for any application, we need to think in these terms as well. A common industry metric then that exists and relates to the title of my talk here is state of health. So state of health is now considering a fresh battery and an aged battery and the comparison between them. So in this case, I didn't use the COMSOL application library example. I went off-piste and did some differential equations of my own design, which will describe in COMSOL Multiphysics the prediction of very slow discharge for a fresh cell and an aged cell. And we can see that the aged cell hits that voltage cutoff at a time which has had less discharge than the fresh cell. And this ratio we call a state of health. So this would be a state of health of 0.85 or 85% approximately. This doesn't give us all the information. It doesn't give us information about power capability. We may be interested in a power profile that is different from the one the battery was originally designed for. So we want to make sure that we really have a good understanding on this. How would we measure this in practice? You would normally measure state of health with a cycling experiment. So you just charge the battery, hold, discharge. We said that the nominal capacity is at low C, so we need to do this very, very slowly. This is a picture of some of the typical kit. I think the color contrast may not show that to you too well, but we have here a multi-channel cycler, so we can study lots of batteries at once, a large climate chamber to maintain constant humidity, temperature, environment, and if we zoom in on the inside of that, we have the battery under study. So you can see that you need a lot of experienced experimental knowledge to set up this type of system, and also it takes a long time to measure this properly. If the industry metric is at 0C, we need to go slowly. We can't go infinitely slowly, but it's a long experiment. 20 hours is too long for people to wait to determine how effectively a battery can be used. We need faster experiments. So the LibForSecUse program is looking at electrochemical impedance spectroscopy. This is a rapid technique by comparison. We oscillate the load on the battery and we measure the oscillating voltage. And like any impedance technique, we will have an amplitude, a ratio of amplitudes between the voltage response and the current load, but also a phase difference associated with the different physical and chemical processes which are involved. And we plot this with this Nyquist plot. And you can think of this really as being like a fingerprint or a signature for the state of the battery. Different physical or chemical properties are identified at different frequency ranges on this plot. And I particularly emphasize that properties like capacity and composition are often associated with the low frequencies in this range. So our interest is, can we use this technique, which is so much faster to perform? Maybe you can get data in minutes to a couple of hours. Will it encode the same information we need about battery health for aged battery analysis? This will be where NPL comes in. So we are the UK's National Standards Laboratory. We are a wholly owned non-governmental institution under a UK-based department. And we support fundamental SI unit definition, calibration, all sorts of things to support industry and quality of life over what the government has identified as national challenge sectors. In battery metrology, we recently published an energy transition report, so I would encourage you to go and have a read of this on our website if you're interested in all of the measurement challenges the battery industry has identified, everything from grid to second use to recycling to materials characterization. And we're trying to support as many of these as we can. In terms of our detailed work and projects, we work in parallel to the UK Faraday Battery Challenge, which was a £250 million investment from UK government in battery research science, particularly driven by the automotive sector. We're active in a government-funded cross-theme project for metrology, in the European project, which this work falls under, and in directly funded Innovate UK projects, so living in that midpoint between business and academia to develop battery second-use applications. So I'll now come in to tell you how my work on this project has played and how I've used COMSOL Multiphysics software, why it has been so helpful to me. So first of all, it allowed me to steal this picture from the COMSOL documentation, which is a nice picture of a typical battery electrode. And we're thinking about aging. What are all the different physical and chemical processes that can cause aging to take place? I was interested in approaching this in a mechanism-agnostic way, so not looking at any detailed or specific chemistry, but just what are the general types of processes that any battery electrode could undergo. We can have disconnection or degradation of material. It no longer stores lithium. It then provides no active capacity. The electrode kinetics could degrade due to surface restructuring. We could have slower transport. The diffusion of lithium could become slower. We could have loss of lithium if it forms insoluble compounds over time, then it no longer contributes to conductivity in the electrolyte. We could have interfacial resistance, and we could have a loss of cyclable lithium. Again, through side reactions, we'll remove the amount of lithium that we can move from one side of the cell to the other. So overall, we can just define an aging configuration, a set of properties, and here we imagine that the state of health depends on the physical condition of the battery in some way. But also, the impedance spectra, which we can measure so much more quickly, also depend on the same physical properties of the battery. So, could we predict state of health from the impedance in some empirical manner? Is there actually a correlation here? That's where we start to think about modeling, to screen, does this even make sense? Is this a good idea? And so we can start from the very standard Newman model as implemented directly in COMSOL's lithium-ion battery interface. You can see a typical model builder tree here. This uses a concentrated electrolyte theory. It uses an extra dimension, so this provides an extra particle dimension, which is helpfully set up for us in COMSOL. We do not need to code this ourselves. All of the theory which it's based on, you can go and read from the group of John Newman. Well, if we want to incorporate our idea about aging metrics into this, all we need to do is take parameters and use parameters to define the condition of aging of a battery. So we just set up some set of aging parameters and then use those as inputs to the lithium-ion battery physics. Then we can take the same physics interface and use different studies. Very helpfully, we can simulate any experiment on that battery using different studies within the same model builder configuration. So if I solve a time-dependent study and I predict a discharge of a battery from start to end, I can identify the real state of health, the analog of the 20-hour experiment, or longer. I can make it infinitely slow in simulation. But I can also get out impedance spectra by solving using the frequency domain perturbation study step type, which allows me to assess those small amplitude perturbations in terms of amplitude and phase. And then if I use COMSOL Multiphysics to generate two data sets, can I identify any useful correlations between them where I could use the easily accessible data to predict the more difficult to access data? Now, I could spend much longer than my allotted time telling you how to simulate electrochemical impedance spectroscopy in COMSOL Multiphysics. All I'll say is it's actually pretty straightforward, and you can go and read COMSOL's own publications for information on how to do this. So, for instance, in COMSOL News 2013, we had work from COA in France about how to do this. You can read a blog a little bit later on the COMSOL website, which will tell you how to do this. I can also always speak to you later, as I'm sure will all the people in red lanyards give you good insight into how to do this. But so let's take a look here at just some simple results. If we simulate that impedance very slowly, and this is a 1D model, but it's a 3D animation, so I cheated. We have here the potential profile, the voltage through the cell, and also the current response. And if we go very slowly, 1 hertz, then the current can respond. So you can see that that current really modulates the voltage response. We get a nice smooth response. If we go very fast, we can predict that we get this rather sharp, more capacitor-looking voltage profile, 2 voltages and a linear field between them. And the current is very, very localized to one surface of the battery. So we really start to get insight into the structural and physical properties of the system. Now, another great benefit for us at NPL of using COMSOL Multiphysics is while it does all of this stuff for me, it doesn't think that it's boss. It lets me be boss of what I'm doing. So I've worked on COMSOL for quite a long time. I consider myself something of an expert in electrochemical simulation in this domain for my years of experience. So I actually want to take control. I want to type in my own complicated equations to make the system run more efficiently, to control the mesh, to substitute some of the built-in expressions. And I'm always allowed to do this. And this has really radically increased the efficiency of a simulation that we can consider. We can move to 3-dimensional impedance simulations with the Newman model, which we haven't encountered from other groups because of this flexibility which is provided from the software. So this is all about how I do it. I'll just use the last few minutes of my talk to show you then some of the results which we've got. We were looking at 6 aging parameters. So to uniformly span that parameter space, we might need 5 to the 6 parameter sets with even a really coarse gridding of how we explore that parameter space. That's too many simulations, even with rapid software and high-performance computing. So we moved to look at what's called a Sobol sequence, or a quasi-random sequence, where we span the parameter space with apparently randomly positioned parameter sets, but ones which statistically uniformly map the space. You can sort of visualize this in 2D, but we can do the same in any number of dimensions, and this allows us to very efficiently explore all limits of the parameter space. So I set this up. I used a MATLAB script to generate the Sobol sequences and to populate a parametric sweep. So there's here 1,000 long strings, or 1,000 entries of specified combinations of different values of my aging parameters, and each differentially aged battery, I will predict both the state of health and the impedance spectra and look for correlations between them. I point out, by the way, that when I showed this to Andrew, he said, why didn't you use a model method to populate the parametric sweep? So those of us who are now a little long in the tooth, we still have much to learn about the capabilities of the software. First of all, let's look at the connection between aging parameters themselves and state of health. We find a really surprisingly good fit just from some simple linear regression on the result. We train with a lot of aging conditions and predict state of health, and then we can put that into new data and get an accurate prediction. Well, of course, there's a scientific connection between the inputs and the outputs of a model. This shouldn't be so much of a surprise. But the really exciting thing is if we look at the contributions to the fit, of those aging parameters, only 2 of them, the X2, the active material loss, and the lithium content loss, actually contributes to predicting the state of health, which makes sense because it's a metric defined with a very, very slow thermodynamically limited experiment, and these are the only thermodynamic properties in the system. The kinetics, transport, diffusion do not matter if you draw very low current. So this industry-important metric, half of the aging parameters I put in, I can predict to high quality without even needing those data. They just don't matter. So if they don't matter, we don't need to record that whole impedance spectrum. So I did the same machine learning exercise with a very selective group of just low frequencies at free states of charge of the cell. And again, we can get a reasonable quality of fit just from a first attempt machine learning in MATLAB post-processing simulated data for impedance as trained into a regression model versus the actual simulated state of health for the same battery condition. So this has given us real confidence that the idea was not a priori ridiculous, that we can pursue this and that it merits further study through our collaborative project. Next steps for us will be to look at further refinement of this fitting, to address actual experimental measurements, which are not so clean and tidy as the results that we get from the simulation in COMSOL Multiphysics, to look at nonlinear frequency response, which can access more information and can also be modeled in the same software, same interface, and to look at some further parameter reduction exercises. So I will finish up here just by giving as many thanks as I possibly can. Obviously, we have to thank our funders in the European Commission. I would like to thank people both in my group and in IT at NPL for being so enabling and supportive of using modern physics-based software in this way. Collaborators in Germany. This is a full list of all of the people from COMSOL support who helped answer my questions over the last 12 months. So thank you to them. They're always so responsive. COMSOL organizers, basically everybody from COMSOL in this room, but particularly Xenia, Richard, and Andrew, thank you for the invitation. And to Svante and Farad, without whom none of us would be here. Thank you for your attention.